morning friends. Today we will going to discuss about the next part in the passband transmission. There is the quaternary phase shift gain, or it is also called as the quadrature phase shift gain. In case of the quadrature phase shift gain is an MRA encoding scheme where n which is equal to 2 and n which is equal to 2 and m which is equal to 2 raised to 2 which is equal to 4. So that therefore with the quadrature phase shift gain, the binary input data are combined into the groups of the 2 bits called as the D bits or die bits, which is called as the die bits, and each die bits is a code is generated one of the 4 possible output phase. There is a plus 45 degree, plus 135 degree, minus 45 degree and minus 135 degree. It is also shows that there is a 45 degree, 135 degree, then 215 degree and 375 degree. In this way we have able to shown there four different phase should be generated. That's why it is called as the quaternary phase shift gain, or it is also called as the quadrature phase shift gain. Then here we have seen the quadrature phase shift gain transmitter. Basically, in case of the any passband transmission or baseband transmission technique, there is a binary input data having the bit frequencies are represented by the FP, and it's the bit clock should be able to provided into the two. There is I and Q. There is a bit splitter, so that here is the I channel and the Q channel should be given. In case of the I and Q channel, the whatever the bit is given the input to the I channel, that will be given the input to the balance modulator, and similarly the output of the Q channel, that is also given to the balance modulator. So that here is the total overall bit should be divided into the 4 parts, means even part and odd part. Basically even part and odd part should be generated with the help of the QPSK transmitter. So that here we have seen the I channel. Here the I channel FB by 2, that will be given to the balance modulator, having the logic 1 is represented by the plus 1 volt and logic 0 is represented by the minus 1 volt. So that what we seen here, to balance modulator the logic 1, similar in case of the logic 1, the is represented by plus 1 volt and logic 0 is represented by minus 1 volt. This input is provided to the each balance modulator, means this balance modulator as well as this balance modulator. But the difference between these two signals is that whatever the reference carrier oscillator will be given to the sin omega ct to the balance modulator along with the logic 1 or logic 0, it will be come to the output of the balance modulator. But here to generate the 90 degree phase shift is created with reference to the original I channel, that will be given to the cos omega ct, and which is cos omega ct, means here is the output is the plus minus sin omega ct. Similarly here output is the plus minus cos omega ct, that will be given to the band pass filter, and both the output of the band pass filter is given the input to the linear summer. Then the output of the linear summer is given to the band pass filter, and which is the QPSK output having. But here in case of the quaternary, or it is called as the quadrature phase shift gain, the total phase is divided into the 4 part. As per the previous slide, here the total phase is plus 45 degree, plus 135 degree, minus 45 degree and minus 135 degree. In this way the total phase is categorized into the 4 parts, which is plus 45 degree, plus the 135 degree, minus 45 degree and minus 135 degree. In this way it will be categorized it. So in case of the QPSK transmitter, what we do, see here, the 2 bits, which is called as the die bits, and are clocked into the bit splitter. After the both bits has been serially inputted, they are simultaneously parallel output. Then the I bit modulates the carrier in phase with the reference oscillator. Hence the name I for in phase. I is represented for in phase of the channel, and the Q bit is a modulated carrier which is 90 degree out of phase with the input channel. Means there is a sine wave as well as the cosine wave. Then for logic 1, with reference to the above block diagram, for logic 1, the plus 1 and logic 0 is represented by the minus 1. So that the two phases are possible at the output of the I modulator, which is switches. There are the two waves. There is a plus sine omega ct and minus sine omega ct. Similarly, the two phases are possible at the output of the Q balance modulator. There is a plus cos omega ct and minus cos omega ct. Then for input of the Q, which is equal to I, which is equal to 1, then input of the two balance modulator are plus 1 sine omega ct. So here for the input of the Q, which is equal to I, which is equal to 1, the two input to the I balance modulator are plus 1 and sine omega ct, and the two input of the Q balance modulator are plus 1, there is a cos omega ct. So its output are to be the I balance modulator, which is to be given here. There is a I balance modulator plus 1 into sine omega ct, which is equal to plus sine omega ct for logic 1, and minus 1 into sine omega ct for logic 0. So in case of the Q balance modulator, plus 1 cos omega ct, so Q balance modulator, there is a plus 1 cos omega ct, which is equal to plus cos omega ct for logic 1 and minus cos omega ct for the logic 0. So the output of the linear summer, whatever the output is coming from the balance modulator, that will be, just we go through this, whatever the output is coming from the balance modulator, that balance modulator is a passes through the band pass filter for both the balance modulator. Once balance modulator is generated as it is, the signal from data is coming from the I channel, and for this balance modulator the data will be, its phase shift is a 90 degree with respect to the above balance modulator, and both the signal is passes through the band pass filter, and finally it will be come to the linear summer. Then in case of the linear summer, what happens? The output of the linear summer, one input is there, which is the diabits, the sine omega ct plus cos omega ct. So this cos omega ct is generally we have to be converted into the sine function, so that in case of the sine omega ct plus sine 90 degree plus omega ct, means it is the same form but in the different way, so that here is the 2 sine omega ct plus 90 degree upon 2 into cos 90 degree upon 2. So what we do here for this case, the root of 2 means we have to be take the square of this, then root of 2 take the square root sine 2 sine omega ct plus 90 upon 2. So what we do here, the root 2 upon 2, okay. Then what we do here, the root 2 means here 2 sine omega ct, basically it will be divided by the 2 and plus 90 degree divided by 2, means here is the 45 degree, means root 2 is nothing but 1.414 sine omega ct plus 45 degree. Means basically the output from the QPSK is defined here. There is a 1.414 sine omega ct plus 45 degree. Then similarly we can calculate it for all other combinations here. Then the truth table should be given here, the binary data and the QPSK output phase should be given here. If the binary data is a 0 0, then your QPSK output is the minus 135 degree. Then for 0 1 it will be represented by minus 45 degree. If 1 0 it will be represented by plus 135 degree, and 1 1 it will be represented by plus 45 degree. Then in case of the phasor diagram, this phasor diagram is represented by the QPSK phasor diagram. On the x-axis it will be able to show plus sine omega ct once the logic 0 is transmitted for the I output, minus sine omega ct once the 0 is transmitted for the output of the I is logic 0, then cos plus cos omega ct when the output logic 1 is transmitted for the Q output, it is the output of the balanced modulator for the Q input signal. And for this case here, for this case minus cos omega ct once the 0 is transmitted in the Q output. So that what we do here for this case, here is the Qi means cos omega ct plus sin omega ct, which is nothing but the sin omega ct plus 45 degree once the logic 1 is transmitted, means here is the 1 1 if your input is the 1 1, then minus cos it is the 1 0, here is the minus minus it is represented by 0 0, and minus 1 it will be represented by 0 1. So what we do here, with the reference of this diagram, we have to be moved for the anti-clockwise direction to show the actual data output. Means suppose here 0 0 0 0 there is a minus minus, 0 1 minus plus, 1 1 there is plus plus, and 1 0 is the minus plus. Means in this way we have to be represent the data in a QPSK form. So in the constellation diagram we have seen that there is a 45 degree, this is the 45 degree for the logic 1 1, here is the 135 degree if the logic is 1 0, 0 0 if the minus 135 degree, the constitution of the Q and I is the logic 0 0, and 0 1 it will be represented by minus 45 degree. So how do we remember? For positive will go and negative will go. I is for sine and Q for the cosine. So silent feature of this scheme is about that each of the 4 possible outcome phasor has exactly the same amplitude. Therefore binary information must be encoded entirely in the phase of the output signal. So the angular separation between any two adjacent phases QPSK is the 90 degree. So that in the QPSK signal can undergo almost the plus 45 degree or minus 45 degree shift in phase during the transmission and still retain the correct encoded information when demodulated at the receiver side. See, this is the output phase versus the time relationship of the QPSK modulator. For this diagram we have shown 0 0, 1 1, 0 1 or 1, means here is the plus 35 degree, the phase shift is given, here is the minus 45 degree, here is the plus 45 degree, and here is the again minus 45 degree. Means basically your output total wave is divided into the different 4 parts. So what is the advantages about the QPSK? See, a very long stream of the data is highly impossible to transmit it. So what we do here to divide the long stream of the data into the 4 equal parts or 2 equal parts, and your data is divided into even data and odd data, and even and odd data should be transmitted simultaneously during the transmission, so that the data security, whatever our main intention about, we have to be satisfied there. And second intention about that, the long stream of the data we have transmitted through the space very easily. So this is the main advantages behind about it, behind that in the QPSK transmission technique. So the bandwidth consideration. So the bandwidth consideration of the QPSK, what we do with the help of the figure, whatever the binary data is coming from the binary input data having the bit frequency is the FB, that will be given to the bit splitter, and your bit should be divided into the two parts. There is a I channel and Q channel, so that your I channel will be shifted at the different way, and the this Q channel is separated on the different way. So that in case of the I channel, this balance modulator what does? Balance modulator is just to receive the one carrier signal along with the digital data. Either this digital data is the logic 1 or logic 0. Here logic 1 is represented by plus 1 volt. Logic 0 is represented by the minus 1 volt. So that according to that, the output of the balance modulator means the output of the balance modulator is generally depends upon the polarity of the I channel, not for the sign. It will be just simply the carrier signal, so that it will be depends upon the I channel. So that what the cos omega ct, the same thing, but only the difference is about that here is to be create the 90-degree phase shift, 90-degree phase shift, that will be given to the balance modulator. So that whatever the output of this balance modulator is totally depends upon the again the polarity of the Q channel. Either it will be transmitted for the logic 1 or logic 0. So that whatever the output will become here, there is a balance modulator, we have to be taken into consideration for the bandwidth parameter. So that here is the input data. So your input data is 110, 110, 10, 110, means it is returned to the 0, means RZ type of the binary data should be provided. So that whatever the I data, once it is the logic 1, means definitely its output should be 1. Here is the 1, definitely here is the 0. If this data is a 0, then your wave is coming towards the negative side for this case. And if logic 1 will become to the here, means here is the again 1 will become to the here, and to maintain here 1. Here is the logic 0, 1, again here 1, means highest fundamental frequency. This is the highest fundamental frequency, and from that highest fundamental frequency your output of the I channel remains it is high. In case of the Q channel is the same here. Once the data will become to the here 1, 1, again 0, 1, and here 1 to the 0. During this the transition is happening just opposite to that. So the highest fundamental frequency at the input and fastest rate of the change at the output of the balance modulator is equal to 1/4 of the binary input bit rate. This is the bandwidth consideration for the QPSK. So in the mathematical analysis we have seen the output is assuming cos omega mt and cos omega ct, assuming until the neglecting the higher frequencies. So we have to be converting this equation cos A and cos B 1/2 cos omega c plus omega mt plus cos omega c minus omega mt. But we know in the previous my video the modulating frequency omega m, which is equal to 2 pi fb upon 4. So putting this equation in the above equation, so this equation is modified in such a way that 1/2 cos fc plus fb upon 4, fb upon 4, because this 2 and 2 gets cancelled out, so that here is 1/2 cos fc, 2 pi fc, 2 pi gets common and that will become outside here, 2 pi fb and fb upon 4 plus cos fc minus fb upon 4. So what we do here, where substitute 2 pi fb upon 4, 2 gets cancelled, and this 2 pi f means here pi f, this pi will be again constant, so we have taken outside, integration should be putting the above equation we get. then fc plus fb upon 4 minus fc minus fb upon 4, then this plus and minus this will be gets cancelled out, fb upon 4 plus fb upon 4, then twice fb upon 4 which is equal to fb upon 2, so that your output frequency should be taken here fb upon 2. Here is the QPSK receiver. In case of the QPSK receiver, what we do here, we have to recover the output, so that input QPSK signal that will be provided to the band pass filter, and the output of the band pass filter is given to the power splitter. So in case of the power splitter, we have to be divided minus sin omega ct plus cos omega ct, because this is the combination of the both I and Q signal. Similarly, in the power splitter, it will be provided for the Q channel. There is a minus sin omega ct plus cos omega ct. Then both the I channel and Q channel that will be given to the product detector. But only the difference is that the power splitter, this is the power splitter, this power splitter is given to the carrier recovery circuit, and the carrier recovery circuit is generated the carrier sin omega ct. Yes, this will be able to provide it same, but here there is a one block we have to be added, one facility to be added here to shift the signal by 90 degree. Is the phase difference between these two signal is the 90 degree, so that it will be created the 90 degree phase shift between the sin omega ct. That's why it will become to the cos omega ct. This is the product detector, so that whatever the minus sin omega ct plus cos omega ct into sin omega ct, and here is the minus sin omega ct plus cos omega ct into the cos omega ct, and this signal is given to the low pass filter, so that minus 1 upon 2 volt should be generated to the here for logic 0, and minus plus 1 upon 2 volt it will be generated for logic 1, so that whatever the output is coming from this low pass filter that will be given to the Q, whatever the output is coming to the I, and which is clock recovery circuit is simultaneously provided to this block. So whatever the binary data should be received alternately, from first odd data should be received and then even data, and it will be able to combine it. This is the operation of the QPSK receiver. Then the output of the product detector, what we do here, see. So I, which is equal to minus sin omega ct plus cos omega ct into sin omega ct, and for the input I, which is equal to 0 and Q, which is equal to 1. So this is the QPSK input signal and this is the carrier. So what we do here, how it will become to the minus 1 upon 2 volt for the logic 0, that part we see here. So after minus sin omega ct plus sin omega ct plus cos omega ct plus sin omega ct, then minus sin square omega ct plus cos omega ct into sin omega ct, and once we have to be modified, this data should be filtered out. Which data? 1 upon 2 cos 2 omega ct and 1 upon 2 sin omega ct. This high frequency component should be removed once it will be passes through the filter. So minus 1 upon 2 plus this all term should become to the 0, 1 upon 2 sin 0 is also 0. That's why the I, which is equal to minus 1 upon 2 volt, this part will become to the here for logic 0. Up to the here we have seen that the quadrature phase shift gain, its modulation, its demodulation, as well as how it will be recovered at the receiver side, how to transmit it, how it will be represented in graphically. Then we have seen here the schematic representation also, its mathematical analysis, that part we have seen. After that, its constantaneous diagram, Then bandwidth consideration, that part is seen here. Then how it will be represented, what is its silent features, just we have take a review here. Then its constellation diagram, its phasor diagram, its truth table, then its output, how it will be represented and what is its equation, that part we seen here. And the basic consideration, the QPSK transmitter, how it will be represent the QPSK transmitter, that part we have seen here. Rather than you have any doubts, any query, please write on my comment page, please subscribe my channel, and you any queries please write on my comment page. Thank you, have a nice day.